We now discuss the solution of a problem from the section Ordinary Differential Equations. And the problem is on boundary value problems. And this question has appeared in CSIR National Eligibility Test held on 26th November 2020, and it is from the section C. The problem is the following 2-point boundary value problem y double dash x, that is second derivative, plus lambda times y of x is equal to 0 for x belongs to the open interval 0 to pi, comma, y at 0 is equal to 0 and y at pi is equal to 0. These are the two boundary conditions. Has a trivial solution y is equal to 0. It also has a non-trivial solution for the four options are given. Option 1, no values of lambda belongs to the set of real numbers. Option 2, lambda is equal to 1. Option 3, lambda is equal to n square for all n belongs to the set of natural numbers n greater than 1. Option 4, lambda less than or equal to 0. Solution. We are given a second order ordinary differential equation y double dash x plus lambda times y of x is equal to 0. Let's call this equation as 1, where we take lambda to be any real number, x belongs to the open interval 0 to pi, and the two boundary conditions y at 0 is equal to 0, y at pi is equal to 0. It is a 2-point boundary value problem. We are looking for the values of lambda for which the equation 1 has non-trivial solutions. We deal with three cases. Lambda belongs to R. We deal with three cases. Case 1, let lambda is equal to 0. Then the differential equation 1 implies y double dash x is equal to 0, and integrating twice we get its a solution y of x is equal to c1x plus c2, where c1 c2 are arbitrary constants, and we use the boundary conditions to evaluate c1 and c2. Y at 0 is equal to 0. That means y takes the value 0 when x is equal to 0. Substituting in this, we get y 0 is equal to c1 times 0, 0 plus c2. So c2 is equal to 0. Y at pi is equal to 0. That is, y will take the value 0 when x is equal to pi. You will get 0 is equal to c1 pi is equal to 0, and you will get pi not equal to 0, therefore c1 is equal to 0. So c1 is 0, c2 is 0, therefore y of x is 0. That is, it is a trivial solution. Thus, we get a trivial solution in this case. We deal with the second case. So that's the differential equation and the boundary conditions. Case 2, let lambda less than 0, that is negative. Let lambda is equal to minus n square. N belongs to R star, the set of non-zero real numbers. Because we have already n is equal to 0 will give you lambda is equal to 0, which we have already considered. Therefore, n belongs to R star. Then the given equation, differential equation, becomes y double dash x plus lambda. Lambda is minus n square. Minus n square y of x is equal to 0. What is this? This is a second order ordinary differential equation, and it is a homogeneous differential equation. So we write its auxiliary equation, m square minus n square is equal to 0. That will give you m is equal to plus or minus n, and the solution, the general solution of the given differential equation is given by y of x is equal to c1 e power nx plus c2 e power minus nx. To evaluate c1, c2, we use the boundary conditions. Now, y at 0 is equal to 0 will imply y is 0 is equal to c1 power 0 plus c2 c1 e power 0 plus c2 e power 0, that is c1 plus c2 is equal to 0, and the second condition y at pi is equal to 0 will give you c1 e power n pi plus c2 e power minus n pi is equal to y at pi, that is 0. And now n will not take 0 value. So n belongs to R star, 0 is excluded. So this way e power n pi, e power minus n pi is not 1. So solving these two, we get c1 is equal to 0, c2 is equal to 0. Again, we get a trivial solution in this case. So for lambda is equal to 0, for lambda less than 0, we get a trivial solution only. So combining case 1 and 2, the equation 1 has only trivial solutions for lambda less than or equal to 0. Let's look at the options. The 2-point boundary value problem has a non-trivial solution for option 4 says lambda less than or equal to 0. It says when lambda less than or equal to 0, it has non-trivial solutions, but we have seen it has only trivial solutions. Therefore, your option 4 is not true. Option 4 is not true. We continue. Case 3. Case 3. Let lambda greater than 0. Let lambda is equal to n square. N belongs to R star. Then the given differential equation becomes y double dash x plus n square y of x is equal to 0, and this is a second order ordinary linear differential equation, and it is a homogeneous differential equation. Write down its auxiliary equation. M square plus n square is equal to 0 will give you m is equal to plus or minus ni, and the general solution of 1 is given by y of x is equal to c1 cos nx plus c2 sin nx. We use the boundary conditions. Y at 0 is equal to 0. That means put in this y is equal to 0 and x is equal to 0. So y is 0, 0, and c1 cos 0. So that is c1. So y at 0 is equal to 0 will give you c1 is equal to 0. Because when n is 0, sin n0 is sin 0 is 0. So therefore c1 is equal to 0. First boundary condition will give you c1 is equal to 0. The second boundary condition will give you c2 sin n pi is equal to 0. What are we looking for? We are looking for non-trivial solutions. So if c2 is 0, again we get a trivial solution, but we want non-trivial solutions. Therefore, to obtain a non-trivial solution, we must have c2 not equal to 0. So c2 not equal to 0, then sin n pi is equal to 0. Sin n pi is equal to 0, n not equal to 0, because n is equal to 0 we have already considered in the case 1. Sin n pi is equal to 0 when n and n not equal to 0 will imply n pi is equal to m pi, where m belongs to z star, the set of non-zero integers. And this means n belongs to z star. Therefore, lambda is equal to n square, n belongs to z star. This implies lambda is equal to n square, n belongs to n, and you get a non-trivial solution. Y of x is equal to c sin nx, and this c depends on n, cn, and cn not equal to 0. So this is a non-trivial solution we got. And how many non-trivial solutions we got? So we got for every lambda value that is equal to n square, where n belongs to n, we get a non-trivial solution. Thus, one has a non-trivial solution for lambda is equal to n square, n belongs to n. Let's look at the options. And our first option says it has a non-trivial solution for no value of lambda belongs to R. This is not true. For lambda is equal to n square, n belongs to n, it has non-trivial solutions. Therefore, the option 1 is not true. And lambda is equal to n square, when n is equal to 1, we have a non-trivial solution. Therefore, this option 2 says lambda is equal to 1, it has a non-trivial solution. And lambda is equal to n square, for all n belongs to n, n greater than 1, it has a non-trivial solution. Here also we have. So thus, further, it has a non-trivial solution for lambda is equal to 1 and lambda is equal to n square for all n belongs to n, n greater than 1. So options 2 and 3 are true. So our final answer is also the options 2 and 3 are true, whereas options 1 and 4 are not true. So that is the solution of the boundary value problem of second order, and it is an interesting problem. I hope that you have understood the solution of the problem. I wish you all the best. Thank you.